Sorry, I kept it. Well, I can tell you now that once I did the same thing, and I was going out of the room after my talk, and then somebody came and told me, "Oh, but you didn't cite my work, and I did this, and I did that," and I said, "No, but your work is not relevant," and the microphone was still on. Nobody heard the speaker. Everybody heard this conversation. This was fairly embarrassing. So this did not happen here anyway. So, okay, so what are the theoretical expectations? The theoretical expectation is that we have a shock near the tidal radius, that and this shock circularizes very quickly. And the implication of this is that if we have an accretion of about solar mass, then with reasonable efficiencies from this accretion disk, we should see something like 10 to the 53 ergs coming out. And if the disk is around RT, which is 10 to 30 gravitational radii, then the typical temperature should be in keV, so it should be in X-ray. And the velocities should be around 50,000 kilometers per second or larger. The typical velocities involved with such a small accretion disk. So this is the expectation. Now, what do we see in this object? And actually, most of my all the talk will be focused on the optical UV transients, and there are also X-ray transients, but I'll be talking only about the optical UV transients. So what do we see here? We see a peak luminosity of 10 to the 44 ergs per second, a temperature of about 50,000 degrees, and the line width of few thousand kilometers per second, about 5,000. And the total energy release is 10 to the 51 ergs. And if you combine these three factors together, then the expected emission radius, just some simple black body arguments, is around 10 to the 15 centimeters, which is about 1000 Rg for this system. So this is definitely not exactly what we see here. And the question, what is happening here? So I want to remind you some old simulations which actually influenced me. This is simulation by Stefan Rosvog, and you see very nicely what is happening. This was actually a neutron, white dwarf around the black hole with few 100 solar masses, and you see the returning stream, and you see the returning stream, and you don't see an accretion disk. Now, it is true there is no precession here, but even so, this is SPH with a lot of intrinsic viscosity. The mass is keep going back to large radii, more or less of the same order of the initial R naught, the initial radius to which the mass was, most bound material was going back, and this does not happen here. So it is clear that at least in this simulation, there is no process that dissipates energy here and produces a shock and produces the disk. And now it is realized, but early on it was not so clear, and there are papers making wrong statement that you have to dissipate angular momentum in order to produce a disk. What you have to do is you have to dissipate a lot of energy to produce the disk. The angular momentum is right there. So that's why the subtitle of this talk is Desperately Seeking Energy Dissipation at RT. So this is what we need. But let's see how much energy I will get from this energy dissipation. And this was already mentioned in one of the talks here. That if you want to form a disk around RT, which is 10 to the 20 gravitational radii, then you need to dissipate Gm over RT. The initial energy of the matter is Gm over R naught, which is practically zero in this compared to that. This is 1000, this is 20, so this is practically negligible. You have to dissipate all this energy, and this is about 10 to the 52 ergs. This is already too much. So because we don't see this much energy. So we need a strong shock here, and this strong shock should dissipate a lot of energy. Now, these are the simulations that Rosen and Hotaka did, and this is the also the logo that we took the logo from this simulation. And so this is the movie of this returning mass here, now with more sophisticated hydrodynamics. And again, there is very little dissipation here at the center. The white regions are the regions where energy is dissipated. And you see here in the simulation that energy is dissipated in large distances from the center, and a very little amount of energy is dissipated near the center. So at least in these simulations, we didn't find the needed dissipation, and this is full GR, but indeed with these parameters the shifts, the upsidal shifts are not so large, so this is still an open issue in my mind what they will do. So what is the observational problem? And I already mentioned it here several times. This is what is expected if you form a disk. If you form a disk, this is what you expect. Temperatures of 5,000 degrees, you see 50,000. Radii of about 10 gravitational radii, you see about 500. Velocities larger than 50,000, you see 5,000. Energy, total energy of 10 to the 53, we see 10 to the 51. So I compare these two numbers, and I call this an inverse energy crisis. It is inverse because usually when you say an energy crisis, you need the energy and you don't have enough energy. Here it's the opposite. There's too much energy in the system, and you see much less than what you expect to see. So this is the crisis, and I want to stress that even the circularization energy will cause by itself, if you circularize, this by itself will cause the same, slightly weaker inverse crisis, because then just the circularization should release 10 to the 52 ergs, which we don't see. It may be coming somewhere, it may be swallowed by the black hole, but we don't see it. So the solution for the where do we see the radiation is outer shocks, and Gilad will talk about this later, and Rosen also mentioned this. It's actually, we suggest that the collision of the incoming stream with the returning material, this is, which happens at about a few hundred to 2,000 gravitational radii. This is the region, this energy dissipation has the right amount of energy at the right time scale and so on, but I will not talk about it. I call this model the what you see is what you get model. You see this, you get it. But let's skip this, and I am just stating that suppose an accretion disk doesn't form, and we see this outer shock, but then we still have this remaining energy. Where is all the energy? Where does all the energy go? Now, one way to hide the energy, and this is the Polish donut model, and by the way, if you show this in Israel, nobody will call it Polish donut, it's called sufganiya, and this is just the time of the year that we are supposed to eat it, and we'll eat it during the conference, don't worry. So this is the Polish donut, and this is the structure of the Polish donut. It's a thick disk, and Oleg here has worked a lot on modifying this model and working out the details of this model. So it's a thick disk. Energy is generated here, but it's all swallowed, advected into the black hole. It's swallowed by the black hole. The problem with this model, it requires a lot of angular momentum to support itself. To have such a structure, you need a lot of angular momentum. And in the system, we don't have a lot of angular momentum because the typical angular momentum is small. Is of order of the angular momentum at the tidal radius, which is small. So it's not clear that you can build such a structure. Now let me remind you something that you probably learned in graduate school. This is the general relativistic effective potential around the black hole. This is how it looks. So what we have here is contours of fixed angular momentum, and this is energy, and this is radius, and these are points of deflection. Each particle on this point was deflected, and this point here, the minimum of the potential, are the circular orbits. And the standard accretion disk theory, the Keplerian accretion disk theory, that Julian described yesterday in the school, but everybody here knows, is that the particle goes from one circular orbit to another, and when you go from one circular orbit to other, you lose both angular momentum and energy, and until you get to this point, which when I was young was called RMS, but somehow it has metamorphosis. It is called ISCO. I don't know why ISCO is nicer than RMS, but this is what happened. So this is the ISCO, and the matter falls from the ISCO to the black hole. And then there's also a question on how fast it forms and what happens here. But basically, this is the end of the regular accretion disk, and the matter falls here. And the efficiency, which is usually estimated, is taken from this value. It's the energy of the ISCO, because you definitely dissipate this, and you may get a little bit of that, but that's a different story. So this is the standard accretion disk, but you can think now about another accretion mode. Suppose that you have a system which is a lot of energy compared to the angular momentum. So you have a lot of energy but little amount of angular momentum. So you will move an elliptical orbit. So this is an elliptical orbit. Now suppose that I take this particle and change a little bit the angular momentum. It will go to this trajectory, go over the top of the potential here and fall into the black hole here without losing much energy. So this is another way to plunge into a black hole without dissipating a lot of energy. So this is elliptical accretion, and this is why I call this the Jerusalem Bagel. Not exactly to scale, but this is something like that. You can put it here, and okay, so this is the Jerusalem Bagel. By the way, you have to eat it with the za'atar, and it is not clear to me what is the physical meaning of the za'atar. So this is an open question for the audience. What is the role of how to add this? Maybe this is the magnetic field. I don't know. So this is a more picturesque way to do this. And so we are talking about elliptical accretion. And what happens is the following, that the question whether you have circularization or elliptical accretion depend on the comparison of the rate of dissipation of energy versus angular momentum. If you're dissipating, most of the dissipation happens here, then here you dissipate little amount of energy and large amount of angular momentum. If most of the dissipation is here, you dissipate lot of energy and small amount of angular momentum. I know that you're standing, I'm just finishing in time. So this is circularization. If you lose a lot of energy, things become more circular. If you lose more angular momentum, things become more elliptical. And now is the question to balance, to compare is this possible? Is it possible? So the mathematical question or the physical question that we ask in this model is, can you dissipate along this bagel more angular momentum more rapidly than energy? If you can do this, then you go to this elliptical mode. If you cannot do this, you circularize. So this has to do with the rate of dissipation of energy, and this is the stresses here. And you can compare it with the rate of dissipation of angular momentum. It's almost the same formula, but here you have this factor of r times t, because which relates the direction of the force and the tangent to the motion. So this is the big difference between these two quantities, and this makes all the difference. Now you can play with these formulas. I don't have time to do all the games here. You replace this relationship by the one of the alpha and velocity. This is the integral of the density divided by integral of the magnetic pressure. This is actually the one of the alpha and speed squared. And you can do these things in both for both the rates of dissipation, and you can go further on with more so this is estimates of the rate, and this is happening, and this is basically the formula that we want, how long it takes to dissipate the angular momentum that we need, and how long it will take to dissipate the energy that we need. And I'll just show this last formula. You can compare these two relationships. They are almost the same, apart from this factor here, which is of order 10. So this rate of dissipation of angular momentum is faster by about, this is the number of orbits that you need. So you'll dissipate the angular momentum in about 10 orbits, while you dissipate the energy in about 100 orbits. This is a very rough estimate, plugging typical numbers here. Most of the numbers do not really matter because you have the same values here and there, but this is the biggest difference. And so we conclude that it is possible, just from this order of magnitude, that this is happening. And so we suggest that this is an alternative. From culinary point of view, this is definitely much healthier than this in terms of calories and so on. This is also a lot of oil. But here, this is low angular momentum, and heat is effectively not generated. This is high angular momentum, and heat is swallowed, both by the customer who eats it and by the black hole. And the conclusion is that the TDE's observations are inconsistent, at least with the simple version of the standard model. You may have to sophisticated versions, maybe, but the simplest version, you have to modify it. This model states that circularization is slow, and it is the energy crisis is naturally solved by elliptical accretion, in which you simply plunge into the black hole with a lot of energy, without dissipation, without converting this energy ever to thermal energy. And of course, there will be some energy, there will be some dissipation, and some of it we'll see in another channel. But this is not the main thing that we see. Thank you. And we have to...
We have time for one quick question.
Why do I get that? Okay, thanks. So it makes sense that, of course, if you basically have an instantaneous impact of apoapsis, your orbit returns to the point of impact, so you will always return to the apoapsis, and that just means you shrink the periapsis. But and you can have basically, eventually have a sufficiently eccentric orbit that you plunge directly and have accretion. The question is, though, in the process of doing that, you're changing the orbit elsewhere. Don't you create stronger and stronger shocks around periapsis as well? So even if eventually all the impact of the apoapsis, before you actually start accreting, don't you have trouble near periapsis?
Yes. Yes, but. So let me reiterate the question. When this is going on, as you become more and more elliptical, suppose that this is happening, as you become more and more action is happening here because the motion is getting closer to the black hole, so you feel stronger GR effect. It will be only at around, you have to get to less than about 10 RG before things get interesting. So if you're beginning at 20, for example, until you get to less than 10, it's not so critical. Once you get to less than 10, then things start to be interesting. And then you get strong deflections, and then this ellipse will be turned, the returning matter will turn, it will interact here or somewhere around here, and may cause something, however, it is not clear what is happening there. And this is, so we think that, in my mind, the question is completely open for detailed numerical calculation, because it is true that you dissipate energy, but you also dissipate angular momentum at this moment. So it is possible that after this interaction, you dissipate energy and angular momentum, and the matter go directly into the black hole. It's not necessarily like this, it is possible. Another thing which is possible, that you generate heats there, but the system is very small, very optically thick, and then you form a small donut inside this bagel, and the donut is does not let energy go out because it's optically thick and so on. So it is true that what happens at the last phases, it's not clear. But the early phases, here, this is mostly supported by this is mostly composed of highly elliptical orbit, this thing here. And the first phase, I think the elliptical idea is working. And I think we just opened the discussion for a new mode of accretion, and now we have to work the details. It may turn out that at the end something else happens.